Hello everyone, let's analyze. So today we're going to talk about differentiation and integration of Fourier functions and a case of the wiggles. We've been looking at a lot of Fourier functions and you may have noticed that they wiggle some. What's up with that? Let's start with the integration theorem. If f is L2, right, which is the bare minimum we need for a function to be represented by a Fourier series in mean, then the antiderivative of f, notice that the antiderivative as we've defined it as the indefinite integral from negative pi to x, that's the particular antiderivative that is 0 at negative pi. That's actually going to be important later on. Of course, we know that antiderivatives, right, form a class that are separated by a constant, the famous or infamous, depending on your experience, plus c. But the antiderivative of little f is the term-by-term antiderivative of the Fourier series of f, where each term of the series is computed using the same indefinite integral above. Furthermore, the resulting representation of f converges uniformly. So let's unpack this theorem a bit. Since f is L2, we know it has a Fourier series representation, where that equality implies that the series to the right of the equality converges to f in mean. And if we were to evaluate this series for any x, right, it's equal to f of x everywhere except for some set of measure 0. In this case, my coefficients, an, are the inner product of f and cosine divided by pi for n equals 0 to infinity. Right? The 0th term is what gives us the constant term of the Fourier series representation. And bn, my sine coefficients, are the inner product of f and sine divided by the normalizing factor pi for n equals 1, 2, and onward. The antiderivative, big F of x, as I mentioned, in particular, the antiderivative satisfying f of negative pi is 0. If I go term by term, I get the antiderivative of the constant term plus, right, the sum of my cosine coefficients times the antiderivative of cosine, right, nx, plus my sine coefficients times the antiderivative of sine nx. And that gives us this expression. A naught over 2 times x plus pi plus, right, this linear combination of sines and cosines and this negative 1 to the n term, which comes about by computing this at the antiderivative of this at negative pi, which is why I get this term. So this representation on the right converges uniformly to f, where f is defined in this way. Right, now you might say converges. What do you mean converge? I don't see a limit anywhere. In fact, there is. Anytime we see an infinity, it implies, right, a limit is being computed, especially if we have an infinity coupled with an equals. Now, when we say that this representation of f converges uniformly, what we mean is that the function Sn of x converges to f uniformly, where Sn is this linear term plus the partial sum of this. So Sn of x as a function converges uniformly to f as big N goes to 0. Right, so notice Sn is not just a partial sum, it's a linear function plus a partial sum. Now that linear function is important. We should caution ourselves. This is not the Fourier series of f. This expression here is not a Fourier series. And it's not a Fourier series because there's no linear term in the complete Fourier family of orthonormal functions. Right? There's a constant term, There's cosine terms of every natural number frequency and sine terms of all these natural number frequencies. But there's no linear term. There's no x function. So this is not the Fourier series. Now, of course, we can take the Fourier series of x and swap it out into here. Here's the Fourier series of x. We've done it before. It's equal to that. So if we take that series representation of x and plug it into here, then we do get a Fourier series of f. But keep in mind that this Fourier series may not converge uniformly. Just because this converges uniformly doesn't mean that if we replace x with this, we get uniform convergence, because this series does not converge to f uniformly. And the reason it doesn't converge to x uniformly, in spite of x being continuous, is that its periodic extension over the entire real line would not be continuous, because you would have to make a jump at the interface of these extensions, right? See our last lecture for examples of that. So if we take this expression of x, plug it into here, and rearrange, then we do get a Fourier series of f. This first term inside of parentheses, this is my constant term, right? Notice that this is just equal to a number. It's equal to a number. This is a coefficient indexed by n times sine, so those are my sine coefficients for the antiderivative f, and here are my cosine coefficients. Notice that my cosine coefficients depend on the sine coefficients of little f, and the sine coefficients of big F depend on the cosine coefficients for little f. And that makes sense because we're taking an antiderivative, right? An antiderivative of sine is a scaling of cosine, and an antiderivative of cosine is a scaling of sine. So let's summarize these ideas as corollaries and bring the integration theorem into focus. Right? Our first is the uniform convergence result. If f is L2 and f is the antiderivative, then I can integrate term by term to obtain this expression for big F, and this expression, which is not a Fourier series, converges uniformly. The Fourier series corollary is that if f and big F are described in the previous corollary, that is, little f is L2, big F is the antiderivative, then I can obtain a Fourier series of big F given by this formula. And in both corollaries, an and bn are as defined as before. Now, these corollaries, right, are a result of the integration theorem for Fourier series. Let's prove the theorem. For example, how do we know that this is even a number? So let's give a proof of the integration theorem. So if we were to integrate the Fourier series of f term by term, we'd get this expression here. But as I mentioned, this is not a Fourier series because of the linear term. So if I take that linear term and just subtract it to the other side, now the expression on the right is a Fourier series. And in fact, we could rearrange it into a Fourier series. We have the constant term, right? Here's a constant, right? There's no function of x here, plus my sine terms, plus my cosine terms. So now on the right-hand side, I have a Fourier series. Does this Fourier series converge uniformly to this expression on the left? Well, let's take a look at that expression on the left. Let's let f tilde be exactly this expression on the left. So f tilde is f of x minus, right, a naught over 2 times x plus pi. First off, f tilde is continuous, right? That's thanks to the fundamental theorem of calculus. Because f tilde is crafted by a indefinite integral, that is an antiderivative of a integrable function, so it has to be continuous, and then we're adding something linear to it. Furthermore, f tilde of negative pi equals f of negative pi. But remember, I chose big F to be the particular antiderivative that is 0 negative pi. Right, minus a naught over 2 times negative pi plus pi. Of course, that's 0. I get 0 minus 0. Now, f tilde of pi is f of pi minus a naught over 2 times 2 pi. Now, f of pi, if we remember the definition of big F, is just the integral from negative pi to pi of f minus a naught times pi. And that's 0. And the reason it's 0 is because the definition of a naught. A naught is the integral of f from negative pi to pi divided by pi. So this pi here and this pi here cancel, and I just get the integral of f from negative pi to pi minus the integral of f from negative pi to pi. So I get 0. So f tilde is continuous and periodic in the sense that it's equal at the endpoints. So we know from the uniform convergence theorem for Fourier functions that the Fourier series for f tilde converges uniformly. Furthermore, after substituting the Fourier series of x into our expression of f yields this formula. As I mentioned, right, we rearrange things so that we have the constant term, we have our sine terms, and we have our cosine terms. Now, a Fourier series is unique in the sense that if you have a function and you have its Fourier series, if two functions have the same coefficients, then they are the same function. Right? They're at least equivalent in the L2 sense. So that means in order to prove that these things do converge and that we actually do have on our hands the correct and right Fourier series, we would have to show that this term equals this term equals this, and this term equals this. So it's a straightforward exercise of integrating by parts and the fundamental theorem of calculus to show that these equalities are in fact true. That is, this constant term is in fact equal to what the constant term of the Fourier series of f should equal to. This term does in fact equal what the coefficients of the sine terms ought to be, and same thing with the cosine terms. We won't get into the proof because, as I mentioned, it's just integrating by parts, and I will leave it up to the viewer. But by showing that these equalities are true, we prove that these terms do in fact converge as they should, and that they're equal to the correct Fourier series. So we actually do get the Fourier series of the antiderivative big F. This proves the integration theorem, and it also proves the two corollaries that follow from it. And just in case you're curious and you want to see how the integration by parts looks like, you can freeze the frame and go over these calculations. I'll leave that to you if you have a Saturday where you want to just get wild. So let's take our theorem out for a spin. Let's look at an example. Let's use the Fourier series for x to compute the Fourier series for x squared. Let f of x equal x. As I mentioned already, we know it's Fourier series. So these coefficients here are what we call Bn. It's the inner product of f with sine of nx divided by pi. We get exactly this value. And in this case, because of the oddness of x, f is just a sine series. So there are no cosine terms, and there's no constant term. So an is 0 for n equals 0, 1, 2, and onward to infinity. So if we apply our Fourier series for the antiderivative result, we get that the antiderivative of x, that is 0 at negative pi, is just x squared over 2 minus pi squared over 2. And plugging Bn into the Fourier series corollary for the antiderivative gives us exactly this expression. This term here, this first summation, that is our constant term. We can simplify because negative 1 to the n plus 1 times negative 1 to the n, we're always going to get a negative, so we have this value. Therefore, if I solve for x squared, because notice x squared over 2 minus pi squared over 2 equals this expression, I get exactly that. I can simplify further by finding a value for this series here, noting the identity offered from Basel's problem, which is the sum of all square reciprocals is pi squared over 6. So I've got 4 pi squared over 6 subtracted from pi squared. That gives me a third of pi squared. And so now I have a Fourier series for x squared. By the way, how does this series converge? Remember, we're not guaranteed that the Fourier series converges uniformly, but in this case we do get that it converges uniformly. That's because x squared is continuous and it's equal at the endpoints of negative pi and pi. So in fact, this expression for x squared does converge uniformly to x squared. Also, this actually is the result of our uniform convergence corollary, right? There's no x term because remember the x term was scaled by a naught and a naught is 0 for this problem. So that's another reasoning we could give for why this actually does converge uniformly. Now, just for fun, we can actually use the constant term of x squared to prove Basel's problem. Recall that the constant term was exactly this expression, and that constant term has to equal the inner product of x squared with 1 divided by 2 pi. Well, the inner product of x squared and 1 divided by 2 pi is 1 over 2 pi times the integral from negative pi to pi of x squared, which is pi squared over 3. So we have pi squared minus 4 times the series in Basel's problem equals pi squared over 3. So if I solve for that series, I get that the sum of all square reciprocals is 1/4 of pi squared minus 1/3 of pi squared, and that is 1/4 of 2/3 of pi squared, or pi squared over 6. So here we have a proof of Basel's problem. There are many proofs. This is one of them. Now, let's go to the Fourier differentiation theorem. Now notice, to take the derivative, we need uniform convergence. Notice, I need f to be continuous, and I need f to be equal at the boundaries. Of course, that implies that the Fourier series of f converges uniformly to f. So we need that as a prerequisite in order to take a term-by-term derivative. In addition, suppose that the derivative is sectionally continuous. So in other words, f could have some corners with jump discontinuities. Then the Fourier series of the derivative of f is the term-by-term derivative of the Fourier series for f. That is, the derivative of f prime is exactly that series there, and that is a Fourier series. Furthermore, if the second derivative exists at x, then the Fourier series of f prime converges pointwise at x. Now, the proof actually follows directly from the proof of the uniform convergence theorem. In fact, we use the Fourier series of the derivative to prove the uniform convergence theorem. The pointwise convergence result follows directly from the, you'll never guess, or maybe you would, the pointwise convergence theorem. So it's a direct consequence of our two convergence theorems. Let's take a look at an example. Let's utilize the Fourier differentiation theorem to compute the Fourier series of the derivative of the absolute value of x defined over the interval negative pi to pi. So notice this function is continuous. It's equal at the boundary. It has a corner, so it's not differentiable everywhere, but it's differentiable everywhere except for a set of measure 0, except at a single point. So the derivative is sectionally continuous. And of course, we know what the derivative of this is. To the left, it's -1. To the right, it's 1. At 0, it's undefined, but its Fourier series will have a value at 0. In fact, we know from our pointwise convergence theorem for Fourier series that at 0, we're going to converge to 0. Additionally, at the endpoint, we're going to converge to 0. Because if we did a periodic extension, that'd be exactly the average of the jump size. Now, since g is an even function, its Fourier series will be a cosine series. A naught is the inner product of g and 1 over pi. Right, so that's 1 over pi times the integral of g from negative pi to pi. And that's just pi. An is the inner product of g and cosine nx over pi. So that's 1 over pi times the integral from negative pi to pi of g times cosine nx, which is equal to this term, right, using integration by parts. We get it's equal to the values there below. It's equal to negative 4 over pi n squared if n is odd, and 0 if n is even. So we only have odd terms. Therefore, the derivative g prime is 4 over pi n times sine of nx, where n goes from 1 to infinity and is odd. Furthermore, we know that this Fourier series converges in mean, and we also know that it converges pointwise in the open interval negative pi to 0 and 0 to pi. Now recall that the function f equals g prime is one that we've seen before, right? Our derivative that we just calculated, let's rechristen it as f. This is actually a function we've seen before. We're going to give f a value at 0. Right, but of course f differs from g prime at a set of measure 0, so we're okay. Let's actually revisit the Fourier series for this function. So here's our function. It's negative 1 to the left and it's 1 to the right. We use this as an example to analyze our pointwise convergence theorem. So we know that, of course, we're going to get a sine series because of the oddness of this function, and that we will converge pointwise strictly between negative pi and 0 and between 0 and pi. But at 0, negative pi, and pi, our Fourier series will remain 0. Right? Notice that every time n is an even number, the Fourier series doesn't change, if you can catch that. That's because it's only changing at odd terms. Now, what's up with those wiggles? Notice how it wiggles. And it does it a lot. There's lots of wiggles. And not only are there lots of wiggles, they don't seem to die down. Remember, in the open interval 0 to pi, and similarly over here, negative pi to 0, I get pointwise convergence. So perhaps it's not uniform convergence, but I would think that those wiggles would eventually settle down. Right, start to flatten out, right, wrap itself around my piecewise constant function, but it doesn't seem to be happening. And so the analytical question we want to ask here is, what's up with that? What's with those wiggles? We know that the Fourier series converges pointwise in the two open intervals that I mentioned. But why don't we see the peaks and troughs of the Fourier series settle into flat lines at 1 and negative 1 for positive, negative values of x respectively? Right? Why doesn't it settle down? Let's analyze this. This is an analysis class after all. So let's let Sn be the partial sum of the Fourier series. So I have a partial sum, so I have a finite sum of sine functions. Now, since the series only has odd indices, observe that if n is even, then Sn of x is just the previous partial sum. So we're going to concern ourselves just with odd n, because for even n, it's the same. So let's find the maximum and minimum value, because remember, we would expect that the max and minimum value would converge to 1 and -1 respectively. Well, where does the maximum value occur? Well, right, this is a problem we've solved in Calculus 1. We'd find the critical points. We'd evaluate our function at the critical points, and from those, find the maximum and the minimum. So a bit of Calculus 1 type sleuthing reveals that the maximum for the nth partial sum is pi over big N plus 1, and the minimum is the negative value. And you can rewind in the video and take a look and confirm that the topmost point of the wiggles and the bottommost point of the wiggles does seem to converge to 0 from the left and right as n gets bigger. And we can confirm that these are in fact critical points because the derivative of our partial sum evaluated at x max is exactly this term. And this term, well, it is 0. Why it is 0? Well, notice that as n goes from 1 to big N, I essentially get evenly spaced points on the interval from 0 to pi. And of course, cosine goes from 1 to -1 in that interval. And because they're evenly spaced, these points are symmetric over the midpoint pi over 2. Let's take a look at a picture. So here we have cosine of n pi over big N plus 1 for big N equals to 1. And for big N equals to 3, remember, we're only taking odd terms of n. Right, so for n is 3, we only have a term 1 and a term 3. But notice I have a positive and negative value, and they're the same because of the symmetry around pi over 2. Right, for n equals 5, I have 3 terms, 1, 3, and 5. 7, 9, 11, so forth. Every single time, if I add up, right, the y value of those red dots, I'm going to get 0 because I have just as many positive as I do negative values in the exact same magnitude. Of course, these aren't the only critical points, but we'll leave it to the viewer to confirm that this, in fact, is a global maximum. And the argument for the minimum value is similar. Now, since for x in the open interval 0 to pi, the partial sum of my Fourier series does converge to 1 pointwise, right? For x in the right, all right, on the right of the 0 in that open interval, we do converge to 1 pointwise. And so we'd hope that Sn of x max would also converge to 1. But that doesn't appear to be the case in our illustrations, right? We see that the wiggles don't seem to die down at all. So let's analyze this. Well, the partial sum of the Fourier series evaluated at its maximal point is exactly this expression here. To help make sense of it, we're going to multiply this expression by 1, but with flair and style. Why did I multiply by 1 in this particular way? Well, because that allowed me to rearrange this into this expression, right? I took, right, half of this 4, right, as the product of 2 and 2. I put 1 here and 1 here. And this n pi, right, kind of went into over here. This pi came over here. This pi stayed the same. This pi went over here. Everyone has a role. I rearranged it in a way because notice I have sine of these values times the reciprocal of these values times this width. So if I look carefully, I see that this actually corresponds to a Riemann sum approximation of the integral of sine t times the reciprocal of t over the interval 0 to pi, where our particular Riemann rectangles correspond to an even or an evenly spaced partition of intervals of length 2 pi over n plus 1. And the heights of my Riemann rectangles are calculated at the midpoint of each partition. Let's take a look at a picture just to make sure that we're all on the same page. So in this picture, I have big N is 9, right? It's, of course, an odd value. And so that sum that we saw is exactly the sum of the areas of the rectangles in the dashed red line. And what we see is that those rectangles correspond to a Riemann approximation of the area under that curve in the blue line, which is the sine of t over t, scaled by 2 over pi, of course. And so if we let n go to infinity, we get that the limit as n goes to infinity of Sn of x max is exactly this scaling of the integral of sine of t over t from 0 to pi. In fact, it's actually not a bad approximation, right? For every part that we overestimate, there's a corresponding part of underestimation. We should get a fairly decent approximation. But the idea is that as n goes to infinity, we converge to this value. Now, is this value 1? It turns out that the value is not 1. Now, because sine of t over t is continuous and bounded, so it's integrable. By the way, of course, the function is not defined at 0, so we just define the function to be 1 at 0 because that's the limit of our function as t approaches 0. So the Riemann sum does converge to the integral. So I get that this is exactly 2 over pi times this sine of t over t integral. Now, by the way, you can't actually calculate this analytically in the sense that you can't take an antiderivative of sine of t over t and just evaluate at pi minus 0. The integral from 0 to x of sine of t over t is known as the sine integral function, often denoted si of x. And here we're evaluating si at pi. So we get 2 over pi times the sine integral function of pi, which is not 1. It's about 1.179 and change. That's bigger than 1. Trust me, I'm an expert. And similarly, when we look at the minimum value, we get negative 2 over pi times the sine integral function. So we get negative about 1.179. And you'll have to take my word that that number is, in fact, less than negative 1. So the wiggles will consistently and always overshoot and, of course, undershoot the left and right values of f at the jump by about 9% of the gap size. So the gap from negative 1 to 1 is, of course, 2. And we're overshooting by about 0.18. Right, so 0.18 over 2, it's about 9% of the size of the jump. So let's revisit our illustration of the Fourier series of our constant piecewise function that goes from negative 1 to 1. And let's see if, in fact, the max and minimum values does converge to what we say it converges. Let's see if we can see that play out. So here I have the same function as before, negative 1 to the left, 1 to the right, and I've marked on the y-axis 2 times the sine integral function of pi divided by pi. And of course, for n equals 1, right, there's our maximum value. Right, so that magenta dot is right at half of pi. And of course, if n is 2, I get the same Fourier series. And if n is 3, right, my maximum point moves to the left. And if n is 4, I get the same function. If n is 5, I again move to the left. By the way, I'm going to get the same wiggles at the right. Because again, our Fourier series doesn't know that we're not looking at a periodic extension. For all it knows, I have this function repeated periodically for the entire real line. It can't tell the difference. So the same max value that occurs here is also going to occur here as we approach this boundary. And similarly, the min value will approach here. And notice that as n gets bigger, we do get closer and closer to 2 times the sine integral function of pi divided by pi, right? So the wiggles, the top peak of the wiggles, never does come to 1. Now, that doesn't negate the fact that we do converge pointwise in the open interval 0 to pi. But always we'll have some value that's about 9% of the gap size above 1. Now, what if we have a different size break? Suppose I have a function that goes not from -1 to 1, but from a to b, and let's suppose without loss of generality that a is less than b. Right? If b was smaller, it'd be the same, but just flipped. Suppose I have this function fab. As I mentioned, it's a to the left of 0, b to the right. But notice that this is just a scaling of our previous f plus a constant. Right? In fact, fab is half the gap size times f plus the gap average. So if s tilde n is the nth Fourier expansion of fab, then s tilde n is the same scaling of the truncated Fourier series of f plus the same constant. Because if I take a Fourier series and scale it, I get another Fourier series, and if I add a constant to it, it's still a Fourier series. So that indicates that the global minimum and maximum occur at the exact same places as before. So if I take the limit as n goes to infinity of s tilde n, what do I get? Well, I get exactly this times 2 over pi si plus this average. So does that overshoot b? Right, b is the larger of the value. It does overshoot b. Right? If this term here was 1, then I'd get exactly b. But if it's bigger than 1, I get bigger than b, and in fact, this value here is bigger than b. Or bigger than 1, I'm sorry. It's about 1.0895. In fact, if I rearrange this, I see that this is b plus the gap size, or the jump size, times about 9%. So I get the exact same result, that my Fourier wiggles are going to overshoot b by about 9% of the jump size. And of course, we get a similar result for Sn at the minimum value, and the limit as n goes to infinity. Right, we get our minimum value of f, minus the gap size times about 9%. So again, the wiggles overshoot and undershoot the right and left values, respectively, of the jump by about 9% of the jump size. So let's put this into a theorem. This is the Gibbs phenomenon theorem. Let f be the piecewise constant function defined there, and suppose that a is less than b. I have a is less than a period. That doesn't make any sense, does it? Look at that, it just corrected itself. Amazing. What was I saying? Yes, the Gibbs phenomenon theorem. So if Sn is the nth partial sum of the Fourier series, right, the truncation to n terms, for odd n, then Sn has a max and minimum at the values we have mentioned before, pi over n plus 1 and negative pi over n plus 1, respectively, where both sides are going to converge to the jump discontinuity as n goes to infinity. And again, if n is even, then Sn is equal to the previous odd term, because the Fourier series only has odd terms. And the maximum of the Fourier series, right, which of course the Fourier series is the limit of the partial sums as n goes to infinity. The maximum of the Fourier series is going to overshoot b by about 9% of the gap, and the minimum is going to undershoot a by about 9% of the gap. And of course, the SI, as I mentioned, refers to the sine integral function that we are evaluating at x equals to pi. By the way, this is known as the Gibbs phenomenon. It turns out that wiggles is not the technical term. Who'd have thunk it? That's all for today.